3 is talking about population proportions and the confidence intervals that we make for population proportions. And this is not that difficult of an idea. If I tell you that there's 1,000 items in a population and 300 of them are right-handed, then what we have is a 30% right-handed population. Does that make sense? And a 70% left-handed population. That's basically what a population proportion is. It says a fraction of the population that has a certain characteristic. Okay. It says, let's say you have 1,000 people in the population and 240 of them are reported to be left-handed, I guess is the scenario we're looking at here. So the fraction of people who are left-handed would be 240 out of 1,000. Okay. The letter P is used for the population proportion. Okay. So we would say that P is equal to 0.240. Okay. The way we determine that, okay, P is always found by taking X divided by N, where X is the number of items that you're interested in. Okay. That's the items that have the characteristic that we're trying to investigate. N is the number of items in a population. Okay. Now, as we move forward, like everything else, okay, we probably won't have access to the entire population. All right. So it says in real-world applications, usually do not know facts about the entire population. Therefore, we have to use sample data to estimate P. Okay. When you see polls on news or on commercials or in a newspaper or in a magazine or whatever, okay, you guys see polls all the time, especially on like social media and stuff like that. You see polls about if there's a big game coming up, like the Super Bowl or something like that. There'll be polls on that. People poll everything. Okay, those are directly related to or are population proportions. Okay, but they're estimates because no poll, and that's the purpose of a poll, is to get an idea of what the population thinks without being able to access the entire population. Okay. It says the sample proportion is called P, and if you look at this, it's got a little like a caret symbol on top of it. Okay, we read that P hat. Okay, it's calculated in the same manner as P, except for we use the data from the sample. Okay, so X will be the items of interest in the sample, and then N, the denominator, will be how many objects were in the sample. Okay. So in a survey of 40 or 4,050 people, 600 of them have a vision impairment. Okay. So what is the proportion of vision impaired people in the local population? Okay. So we don't know the local population. Okay. It's greater than 1,000. Okay. It's greater than 4,500. That's our sample. So the population is obviously bigger, right? Okay. But of those 4,500, 600 of them are vision impaired. Okay. So our P hat, okay, our proportion of the sample that is vision impaired would be 600 over 4,050, which changes to 0.148. Okay, and that repeats, so it's 0.148, 148, 148, 148. So we call that P hat. So occasionally, text will use P prime instead of P hat. All right, that's just something that author to author is a little bit different. Some I was, trying to pick out videos for you to watch yesterday that introduced this. A couple of the videos. Instead of using P hat, we're using P bar. Okay. Regardless, there's a differentiating feature to explain or to show that P hat, prime, or bar is different than just P. Does that make sense? Okay. So it's eliciting that we're dealing with the sample proportion and not the population proportion. Okay. So at its root, the population proportion is a binomial distribution. So remember binomial distributions. Binomial distributions were you had two outcomes, and this is where polls are basically population proportions. Because if I'm being surveyed in a poll, whether I like candidate A or candidate B, it's either I'm favorable candidate A or I'm favorable candidate B, right? Does that kind of make sense? Okay. Either I think this team's going to win or I think it's going to lose. There's only two outcomes. Okay. So there's only two possible outcomes: successes or failures. Okay. So basically, voting for one individual or not. Okay. It's a success equals item of interest. Okay. So there is a fixed number of trials. That's the sample size. Okay. So in our last one, you were either visually impaired or not visually impaired, right? There's your two options. Okay. Sample size was 4,050 people. There is your fixed number of trials. Okay. And the probability of success is deemed to be constant for each trial. So N is the number of trials, P is the probability of a success, Q is the probability of a failure. Okay. And now I'm using P and Q. Those are from the population. So some common notation that we're going to use here. This comes from a sample. Okay. So P is equal to population proportion. That's the thing that we're going to try to estimate because we don't know the population. Okay. P hat then is the sample proportion. Then P hat found by taking X divided by N. Q hat is N minus X over N. Okay. I don't really like that formula because there's an easier way to do it. If I have if P hat is 30%, then Q hat is 70%. Does that make sense? Okay, they're complements of one another. Okay, so P hat and Q hat. And if you remember back to working with binomial distributions, I forget what chapter that was. It might have been chapter 4. We used P and Q in that same fashion. Okay, P was a probability of success and Q was a probability of failure. They are complements of one another. It's up to you. Some text will show it. You might see it, like if you're doing a viewing example or something like that in the homework, and that pops up. Maybe you have something to look at to realize what that means for that problem. So we use these things in polls quite a bit. Biologists use these a lot when trying to figure out, like endangered, especially with endangered species. Like if we want to know how many blue whales there are. Okay, well, it's impossible for us to call a blue whale meeting and they all show up, right? Okay. So they will go out and they will tag so many. It's called capture, recapture. They will go out and tag so many blue whales. Okay, and once they tag, let's say they tag 1,000 blue whales, they then say that is their population. Okay, they go back out a second time and they try to tag more whales. Okay, the hope is that some of those whales the second time that they tag already have a tag on them. Does that make sense? Okay, so that they get recaptured. Basically, then we say that we can use that 1,000 as the population, and if I use then in that second capture, I see maybe we get 30 whales that already had a tag on it. We can use that information to get an estimate of how many blue whales there are in the population. Does that make sense? Okay. So biologists use this all the time. Or conservationists use this all the time. It's very useful. Okay. So here's an example. It says in a study of 200 people, they were asked if they were satisfied with their job or profession. Okay. So it's a binomial. Okay. Fixed number of trials, 200. You have two outcomes. Yes, I like my job. No, I don't. Okay. It says 162 people responded favorably to the question. Okay. So the question was, were you satisfied? They answered favorably to that, so they must have said, yes, I'm satisfied. Okay. So N was 200, X is 162. Okay. And if I take X divided by N, we get 0.81, correct? So 0.81 is our P hat. What that means to us is that we can say that 81% of the people are in the population satisfied with their job. Okay. Now, if I took another sample of 200 people, will I get 81%? Most likely not, right? Okay. In all actuality, I could take another 200 people and I could probably get 30%. Okay. We could get different point estimates. Does that make sense? Okay. So P hat is 0.81. Q hat then, obviously, if 162 people were in favor of it, that means 38 said no, they don't like their job. 38 out of 200 is 0.19. And that is exactly, how did I find that 38? I took N minus X, right? That's this formula right here, N minus X. Or, what I think it would be easier, if I know 0.81 said yes, then the complement should be 0.19, and they said no. Okay? Notice that P hat, Q hat do total 100% or 1 in this scenario. Okay? So as was true with means, okay, and that's what we just got done working with, right? Trying to estimate mu. Okay? Now we're trying to estimate population proportions. Okay? So as was true with means, given a sample proportion, we try to estimate the population proportion. So point estimates and interval estimates for a population proportion can be made by using the sample proportion. Okay? So what we just came up with in this particular population, we said 81% favor their profession. That's a point estimate, okay, which provides us really no degree of accuracy for how good that answer really is in comparison to the entire population. Does that make sense? Okay. Point estimates have no essentially degree of accuracy attached to them. And that's what this says here. So yet, like we saw with means, a point estimate does not allow one to determine how good P hat estimates P. Okay? P hat of 0.81 might not even be anywhere close to P. Okay? Might be spot on. Okay? But it might be very, very, very different. Okay? So what do? We turn to interval estimates instead. Okay? So the confidence interval for P is based on the sampling distribution of P hat. Okay, this is when the sample size N is no more than 5% of the population size. The sampling distribution of P hat is approximately normal. That's something we learned actually back when we were talking about binomial distributions. Okay, you see here it says from previous sections, we learned that a binomial distribution can be approximated by a normal distribution if N times P is greater than or equal to 5. And N times Q is greater than or equal to 5. Both those conditions are met. Then we can basically say that this distribution is approximately normal. Okay, and so close to being normal that we'll use the normal distribution to figure out this interval. All right. Up here it says we'll have a mean of P and a standard deviation of the square root of PQ over N, square root of PQ over N, where Q obviously is 1 minus P. Okay? Now that's if we knew everything from the population. Okay? So we're not going to know things, we're not going to know P and Q. We're going to know P hat and Q hat. So they're the best replacements for P and Q. Does that make sense? So that's why you see down there in the confidence interval formula, okay, confidence interval formula down here, that our best estimate for P is we start with P hat and we remove our margin of error, which is that Z sub alpha over 2 times the square root of P hat Q hat over N. And on the right-hand side of the inequality, we then add that to P hat, and that's going to give us our interval. Okay? Kind of talk about this. So some formulas, some textbooks, just like what we did with mu, will say this. They'll say, no, we're going to go P hat minus E less than P hat plus E. Okay? E then is defined as Z sub alpha over 2 P hat Q hat over N. Okay? Now here's the thing, and this we saw a question, I think it might have been question 15 on the quiz last week. They gave us a scenario that said something to the effect of, like, they gave you an interval, like I'm just going to make it really simple here. If my interval is 5 to 10, they ask you find what mu is, and they ask you to find what the margin of error is. Basically saying what is the point estimate, and then what is the margin of error. Well, when we do this, think about this. Did we start here? Did we start with the same thing on both sides? That makes sense? Okay. So when I subtract E and add E, that means that I have moved to the left a certain distance, and I've moved to the right a certain distance from that P hat, correct? Okay. So when I create my interval, so essentially here's the idea. We started at P hat. We moved that distance to the left when we subtracted E. We moved that distance to the right when we added E. Does that make sense? And it gave us that new interval. Okay. Well, then if I'm given that interval, which is 5 to 10 now, how do I get back to figure out what P hat is? P hat has to be where in this interval? It's got to be in the middle. And the way we find a midpoint, several ways you can do it. The easiest is to add these together, divide by 2. Okay. So if I add together, divide by 2, I get 7.5. So that would be our point estimate in this sample. Okay. If it's 7.5, then what is the margin of error? If 7.5 is smack dab in the middle, that's 7.5 right there, that P hat. What do I need to add to get to 10? 2.5. So 2.5 is my margin of error. That's that E value. Does that make sense? Okay. So we didn't do that directly, but my hope was that we were like that's like an Algebra 1 concept. Okay. So another way to find that midpoint is to subtract those. You get 5, and then cut it in half, right? You get 2.5. Okay. But 2.5 is the margin of error, so we're going to have to add that to 5 or subtract it to 10 to get that middle value. Does that make sense? That point estimate. So we're going to do the same thing here, and they might ask you that in a couple questions in your homework. Yeah. All right, so it says collaborative learning in college helps students prepare for life in business world where employees are required to work together in teams. Community college survey student engagement reports on the proportion of students who have worked with classmates outside class to prepare a group assignment during the current academic year. So suppose that a random sample of 300 students. So what is that? 300 is what variable down there? Huh? No. Sample of 300, that's N. Okay. So 300 students is polled. 174 students reported that they did indeed work on a group project that year. That's X. So P hat, okay, we're interested in how many people worked on a group project together, right? So P hat is X over N, which in this case would be 174 over 300, right? Okay. So P hat then turns out to be, if we divide that out, P hat becomes 58%. Okay. But we have no degree of accuracy for that. Okay. We can't be very confident with that. Okay. So it says, however, different samples of students may most likely turn up different sample proportions P hat. So if I choose another 300 people from this college, okay, in which some of those that were in the first 300 might show up in the second 300, okay, but if I do that, I'm probably going to get something different than 0.58, okay. If I do it again, I'm probably going to get something different than that number, okay. So these point estimates carry no measure of confidence in their accuracy. They're probably close to P, but it is also possible that they are nowhere close to P, okay. So the only thing we can do is do a confidence interval, okay. Now, in order to do these, in order to make sure that we can construct a confidence interval, is that we have to make sure that N times P is greater than or equal to 5 and N times Q is greater than or equal to 5. And what that will do is guarantee that the distribution is approximately normal. Okay? If we can't get N times P or N times Q to be greater than or equal to 5, then we can't do the problem. Does that make sense? Okay? So if I look at this, I take N, which is 300 times P, and I want to make sure that that is greater than 5, and then N times Q, make that equal or greater than 5. And it's actually P hat, Q hat, because we don't know P and Q from the population. So then we take 300. P hat was, what did we just say it was, 0.58. And then we're going to take 300 and multiply it by 0.42. And you obviously see that, 300 times a half would be 150, right? So this is obviously greater than or equal to 5. 300 times 0.4, so 300 times 4, or 3 times, so that's going to be like 120-ish, right? Does that make sense? Okay, so that's greater than or equal to 5. So we do meet the condition that the distribution is going to be approximately normal. So then all we have to do is plug our information into this formula where we take P hat minus our error is less than P hat plus our error. And all we got to do is, we know what P hat is. P hat is 0.85, right? We got to find our error. So our error is found by taking Z sub alpha over 2, square root of P hat, Q hat over N, and we'll pick up with that tomorrow. You could probably maybe navigate a little bit. I think it's like 12 questions on your homework. You can navigate through some of that. It's not due tomorrow. We'll pick up with this on or during class tomorrow, and after class tomorrow, you should be able to finish that assignment then.